All right, so your warm-up question for today are really questions. You have two. The first one is a calculation, and it says find the frequency of a light wave with a wavelength of 6.43 times 10 to the negative 7th meters. I'm actually going to answer the second question first, and then we'll go over the math. So the second question says, what is the significance of the photoelectric effect in our understanding of light? Okay, we talked about the photoelectric effect yesterday. And so what did the photoelectric effect tell us about light? Maybe you looked at yesterday's notes if you don't remember. But what did we learn from that?
Something to do with like photons.
Something to do with photons, yeah. Okay, something to do with photons. The photoelectric effect was that definitive proof that light was behaving as a particle, and photon is the name of the particle, yes. Okay, so that's what you need to talk about with that second question, is that it was showing, the photoelectric effect showed us light behaves as a particle, not just a wave, and that's again how we got to the current model where we have this wave-particle duality. It's both at the same time. Okay, number one is a calculation, so let me go ahead and go here so we can work it out. The information that's given to us, we have a wavelength of 6.43 times 10 to the negative 7th meters. And although it's not in the question, we know the speed of light. It's a constant, 3 times 10 to the 8th meters per second. It really should say a light wave because it doesn't actually specify. But I'm going to tell you that this is an electromagnetic wave of some kind. Okay, and so we have the wavelength, we have the speed of light, we're looking for frequency. And our equation is this one, speed of light equals wavelength times frequency. And so if we substitute into that equation, we have 3 times 10 to the 8th equals 6.43 times 10 to the negative 7th times f. If we want to solve for that frequency and get our answer, we just need to isolate that variable, which means we need to divide both sides by 6.43 times 10 to the negative 7th. And when we do that, we get a frequency of 4.67 times 10 to the 14th hertz. Okay, so that is your frequency that you should have for this particular answer to the warm-up. Okay, so you should be able to solve for that using the equation that we learned earlier. All right, any questions about the warm-up? Yeah, if you're typing this in MyOpenMath, you can type 4.67 and then a capital E and then 14. Okay, that would be how you would enter that. All right, so again, please make sure you have these in MyOpenMath, and then we're going to go into our notes for today. Today is the last bit of notes that we have on light, and really today we're talking about optics. And so we're going to go through some notes. You are going to want to write this stuff down. Some of this is a little bit more confusing than some of the stuff we've done previously in this unit. So let's start by talking about how our sight works. Okay, and we've mentioned this already. We are able to see objects around us due to light rays that are made by those objects or reflected off those objects. I talked about that the other day, those illuminated versus luminous objects. And that some of these objects make their own light, some of these objects reflect light, but in the end, the way that we perceive them and see the world around us is due to these light rays leaving these objects, whether the object makes its own light or is reflecting light, and makes its way to our eye. Okay, the light rays converge inside of our eye, and an image is projected on our retina and is then interpreted by the optic nerve, and then of course you see whatever that object is. Okay, your eye has a built-in lens in it. You can see it in the picture right here, which allows those light rays to converge. And we're going to talk about lenses today, and we're going to talk about mirrors today as we go through optics. But again, a lot of the stuff we're going to talk about can be applied to your actual eye, not just a lens like in a magnifying glass, but your actual eyeball has a lens inside of it too. But we're going to start with mirror. So let's talk about reflection in a plane mirror first. So a plane mirror is simply a flat reflective surface. So like the mirror in your bathroom, as opposed to like a funhouse mirror that has like weird shape to it. A plane mirror is just a flat, normal, boring old mirror reflective surface. And so whenever you have light rays that strike this flat surface, we still follow the law of reflection that we learned in the last unit for mechanical waves. And that states that the angle of reflection equals the angle of incidence. And so what that means is that if the incident ray strikes the surface of the mirror, then the reflected ray will leave the surface of the mirror at the same angle as measured from the normal line. We talked about the normal line yesterday. It's an imaginary perpendicular line that you draw to the surface of that boundary. And so here's these equal angles. So if you have a bunch of light rays striking a flat surface, you'd have an image that looks like this. Now if it's not a flat surface, of course you're going to get more scattering of the light because it's still going to follow the law of reflection, but now the surface isn't flat, and so the light kind of gets dispersed in all these different directions. So we're not really going to deal with this. We're going to deal with flat surfaces that do things like this or like this. Okay, so we're not going to worry about that last one. All right, so in order to view an object, you must have a straight line of sight to that object, and when you do, light will come from the object to your eye. If there is something between you and the object you're trying to view, you cannot see it. It's not like sound. The waves aren't going to bend around the object so that we can see it. Okay, we can't observe these images by diffraction. So like if you've ever been at a concert and there's like a really tall person in front of you, or maybe somebody sitting on somebody's shoulders, you don't have a very good view anymore. You can still hear it, but you can't really see it. Okay, so you have to have a line of sight, okay, which is what this is showing here. So here's how an image appears in a mirror whenever you look at yourself in the morning while you're getting ready. Okay, for example, light reflects off of all objects in multiple directions that can be traced to a point inside the mirror. This is called the image point. Okay, so here's an object, and here's, I guess, 3 different people that are just eyeballs looking at this object in a mirror, but you can see in all cases that you can trace this line to this back of the mirror where they converge and make this image point. Okay, so this is the image point right here. It is behind the surface of the mirror. You can't touch it. It just looks like it's behind the mirror. When you look in the mirror, it looks like you're inside the mirror. Okay, the rays that strike the mirror bounce off at equal angle, and some of them will reach the eye of a viewer who will see the image behind the mirror. Okay, so you can see how these light rays, if you follow this blue arrow from the object, this is the light coming off of the object, and then it bounces off the mirror to this person's eye. Or this light ray bounces off the mirror to this person's eye. Or this one over here, same thing, bounces off the mirror to this person's eye. Okay, so as long as you can trace a ray from the object to the viewer, okay, then it can be seen. So as long as you can draw this bouncing off and it hits the mirror, then you can see the object in the mirror, and you would see the object back here at this image point. But this is known as the line of sight principle, so you have to have a line of sight to it. Okay, now images formed behind a mirror are called virtual images. You do need to know the difference between a virtual image and a real image, so I would definitely write down these vocabulary terms in your notes. Okay, a virtual image is produced when rays appear to converge but do not actually meet. I'm sure you guys already know this, but you're not actually behind the mirror. Okay, the light doesn't actually go back there. Your brain interprets it that way. It appears to do that. That's what makes it a virtual image. So when you look in the mirror, that's just a virtual image. There's nothing actually back there. You just perceive it to be back there. Okay, so virtual image is different than a real image. A real image occurs when rays converge. This cannot occur with a plane mirror. You're not going to get a real image by looking in a flat mirror because the light doesn't actually go inside or behind it. You can get a real image with different types of lenses. In fact, you do. That's how your eye works. And you can get a real image with a curved mirror, which I can show you in a minute, so you can see the difference between a virtual image and a real one. Okay, but here are some image formation characteristics for a plane mirror. Okay, images are virtual. Again, they're not formed by the convergent of light, only the apparent convergent rays that, again, your brain interprets to be back there. There is a left-right reversal of the image in a mirror. I'm sure you know that. If you're standing in the mirror, everything is flipped side to side, left to right. In fact, if you look up here at this picture of this ambulance, and maybe you've never noticed this before, but a lot of emergency vehicles have the words printed backwards, so that when you look in your rearview mirror, it says ambulance forward, okay, because it reverses it left to right. Okay, so again, left-right reversal. Images are oriented in the same vertical direction as the object, so it doesn't flip them vertically, it only flips them side to side, which again you know because you know you're not upside down in the mirror. Images in a plane mirror are the same size as the object. When you're looking at yourself in the mirror, your reflection is the same size as you, and it appears to be the same distance behind the glass as you are in front of the glass. Okay, and that's this last one. Images are located behind the mirror, and the image is the same distance behind the mirror as the object is in front of the mirror. Okay, so again, those are just some image formation characteristics for a plane mirror. So again, I'll give you a moment to write those down if you're trying to copy them down still. This, by the way, is slide 63 in case I'm going too fast. All right. So in this diagram, 3 individuals are viewing an image of an object along 3 different lines of sight. Each person sees the image due to the reflection of light off the mirror in accordance with the law of reflection. When each line of sight is extended backwards, they will intersect at the same point. This is the image point. We already talked about that, but that's how they're getting it. If you can trace this reflection and follow that law of reflection, and then you can trace it backwards, you'll reach the image point behind the mirror. All right, so this is the type of question you're going to see. Okay, so in this diagram, can the boy see the image in the mirror? So if this is the boy over here, and here's an object, and here's my mirror, would this boy be able to see this object in the mirror?
Yes.
Again, all you have to do is see if you can draw a reflected ray, and if that reflected ray hits the mirror's surface, then yes, he can, and he absolutely could. Okay, you would be able to see that object. In fact, he would be able to see that object appear right here. Okay, this is where the virtual image would appear behind the mirror. Okay, so yes. Okay, what about now? Can he see the object?
No.
Nope. You would not be able to see that object in the mirror because, again, you can't draw a ray bouncing off the surface of it to get to his eye, at least not one that's in accordance with the law of reflection. Okay, or if you draw that line of sight, it does not intersect the mirror. What about now?
Yes.
Yep, and it would appear right there. Okay, so again, you should be able to figure this out, but again, if here's your object, your virtual image is going to appear the same distance from the mirror, pretty much in line with it. So if you can trace a line of sight like this and it crosses the mirror's surface, you can see the object. All right, so that's mirrors. Okay, plane mirrors are pretty easy. Okay, lenses are a little bit trickier. So we're going to talk about convex lenses. This is the type of lens that is in your eye. Okay, that you use to see. It's also the type of lens that you would use if you used a magnifying glass. Okay, a convex lens curves outward like a sphere, and you can see that here. It bends outward on both sides, and it bends light in the direction of a focal point, and it is used in things like eyeglasses and microscopes. It's also, again, in a magnifying glass. This type of lens is also called a converging lens because it focuses light passing through it to a point. So it causes the rays to converge, and again, this is what is happening inside of your eye, where this image converges, or where this focal point is where the image is projected on your retina. Hopefully, if it's not, you need glasses. Okay, and some of you probably have those, or contacts. Okay, because that's how you correct that. So again, you'll see pictures of them like this, but they cause light rays to converge. Perhaps you've even played with a magnifying glass to cause light rays to converge to try to set something on fire. It's always in the movies, like the boy, like Toy Story, who like tries to burn Woody's face or whatever. But you see like kids burning ants and stuff like that. I'm not suggesting you do that, but it is something I'm sure you've seen before in movies. Hopefully not in real life. Please don't go torture the bugs. But you can see that it does converge those light rays to a point. Okay, and that's also what this image is showing here, and this image is showing the same thing. Again, these are called converging lenses because they cause light rays to converge. All right, so here are the parts of a convex lens. You do want to label these because you're going to have to be able to draw a diagram in a minute. So you can draw this picture on your paper. I'm just going to go ahead and click through so they're all on the screen so you can copy them as we talk about them. But point A, which you can see over here, is you can label it as C or as 2F. It is called the center of curvature. Point B, which you can see right here. Notice that A and B are on both sides of the lens, by the way. It depends on which side the object's on. But point B right here is the focal point. Point C in the very center is known as the vertex, which kind of makes sense because it looks like the intersection of two axes right here. But this is our vertex, which is labeled as an O. Point F, and it's not really a point. Actually, I don't even see F labeled on here. Is the focal length. Oh, it's D. Sorry, it's point D. I was like, there's not, the F is over here. That's not what I want. I want D. This right here is the focal length. It's represented by an F. Sorry. So the focal length is the distance from the vertex to the focal point. Okay, and that's represented here by this arrow that's labeled with a D. The arrow that's labeled with an E, this longer one that goes from that vertex to the center of curvature, is called the radius of curvature. And then F over here, this whole horizontal axis is called the principal axis, and G right here along this dotted line is called the optical axis. I'm going to tell you right now, I'm not going to ask you a bunch of questions about all these things, but the most important ones for you to know are 2F, F, and then your focal length. Okay, those are the ones that you're really going to see in a minute with the ray diagrams that we're going to draw. But it would be helpful to have all the parts labeled. So again, you can draw this on your paper and label these things. I'm going to give you all a moment to do that so that you have it in your notes so that you can use it whenever we go over this in just a moment. All right, hopefully you've got that all labeled down. Okay, so we're going to talk about real versus virtual images because I know I've given you the terms already. But what is the difference? A real image is formed where light rays are focused on the other side of a lens. This happens when the object is farther away from the lens than the focal length. So if the object is past that focal length, past the focal point, then you'll get a real image formed. Okay, a virtual image, on the other hand, is an image from which the light rays appear to come, but they don't actually come from that image. It's on the same side of the lens. This can happen when the object is closer to the lens than the focal length. And again, a virtual image is what we talked about with a mirror as well. With a plane mirror, you get a virtual image because the light rays don't actually go back there. So again, if it's not where light rays are actually converging, but they appear to converge or your brain interprets them that way, then you get a virtual image. If they do actually converge, then it's real. Okay, so real images, I'm going to show you this video clip about real images, and this is a camera obscura in the back of a U-Haul, but this is how your eye works as well, and this is how you can make a real image with a lens.
Yeah, when are we gonna do the science?
Hey, I'm Diana, you're watching Physics Girl, and we made a camera obscura in the back of a U-Haul. So last week, I held a meetup in San Diego with donuts and science, which attracted some awesome people, including the star of the show, Lily. This is a director right there. The meetup was super fun, but the purpose was to make a massive camera obscura that you could get inside. So I got this idea from the guys from the channel earlier in the summer, and we had made this U-Haul contraption, which was awesome. You get to see it? The reason that the channel How to Make Everything wanted to make the camera obscura was because they were, in the end, making a camera. I'll tell you a little bit more about that video at the end of this video, but you should definitely check it out, and I have a link to it in the description. So I decided it'd be fun to get some reactions. So again, we covered the back of the U-Haul with cardboard and tape so it was completely dark inside, except for a single hole, and invited people out to experience this massive camera obscura with us. Are you ready? Yeah. Johnny wrote system IQ. Oh, okay. I'll come over there. Lock us in. Alright. So ominous as it closes. There we go. Oh, that's so cool. Wow, that's really cool. I know. Stan, can you wave your arms? As your eyes adjust in the dark, the first thing you notice is that the image is upside down. How did you do that?
On the sides, too.
Yeah. Oh, man, you can see the scene the whole way around. Awesome. With the trees over there in the corner. Oh, wow, that's cool. That was people shining their phone lights at the back of the U-Haul from the outside, which must have looked hilarious from the outside. Wow. anything about it? Or?
Because when we saw the image on the right side of that, that came in really clear.
Jake, can you like turn in a circle? Yes.
All this stuff out here is like in there, but like flipped and upside down and also backwards, and it's really just awesome.
You can also pan to different
Oh yeah.
Let's over here.
You see
Quick side note, my friend Dan and I liked this experiment so much that we decided to redo it a third time, but this time put the camera in the back of the U-Haul and hang a sheet from the ceiling a few feet in front of the hole so we could do this. This is our moving U-Haul camera obscura. What did you think? Good?
I want to tell some people around the park around us.
And a science communicator is born. So what is a camera obscura? Well, the name suggests that it's camera, like chamber, obscura, like dark. So like a dark room. It's kind of what it is. It's like a projector, but you're not using a light bulb, you're using ambient light, and what's projected on the back of the chamber is upside down, backwards, and pretty dim. It's something often used by intro art classes so that they can set this up and trace the image. As you'll see, the camera obscura explains a lot about why our eyes are made like they're made and how they work. Okay, so how the camera obscura works, it's kind of like your eye in that there's a hole, like the hole in the cardboard or the hole in your eyeball, your pupil, that lets in some light to project on the back of the U-Haul or the back of your retina. The key to how this works is figuring out why you need the tiny hole. Why doesn't an image just project itself nicely on the back of an open box? It's not a dumb question. Okay, imagine trying to image or project this vertical rainbow poster. We're first going to shine light on the poster because we need to be able to see it. And now if the box were wide open, let's see what we would get projected at the top of the box. The light we're shining on the poster would bounce off, and then you'd get green light and red light and yellow light and all the light rays going to the top of the box. So at the top you'd see a blur of all the colors. But if I start to block out some of the rays by making a barrier with a small hole, eventually the only thing getting through to the top of the box is a ray from the bottom of the poster, a purple ray. So the top of our image will look purple. Now look at where the rays from all the other colors go, and you'll see they end up projected on the wall in order, but from bottom to top. So we have a perfect image projected on the wall, upside down. It's also backwards, because if we did the same process with the poster sideways, the colors would be flipped horizontally. But it's not actually a perfect image, because if you look really closely, some of the colors bleed together a bit because our hole has some width. So that means the smaller we make the hole, the less those colors will bleed together, which translates optically into a sharper image, but it also translates into a dimmer image because less light is getting through. So the hole, in the end, keeps the light in order. Your eyes and most camera lenses do this with the help of a lens, which allows you to let more light in, but then it has to bend the light to keep the light in order. The camera obscura doesn't have a lens, so it doesn't bend light. Therefore, the opening has to be super small. Using this same principle, if you're nearsighted and you can't find your glasses, you can use tiny slits in your hands to peer through and focus. Minute Physics has a great video on why this works. Basically, optics is lit. Now the hole in our U-Haul was obviously not that small. It wasn't a pinhole. And because of that, the image is a little bit blurry. In fact, when we opened the hole up wider, you couldn't make out nearly as much detail, but you sure could see better. It was amazing how much of the scene we could still see. Historically, people used camera obscuras to study the sun. Since you can't look at it directly, you could project it onto something else. It was pretty awesome to realize the first time we saw that super bright spot that it wasn't light coming in from some crack. It was the sun projecting sideways through the hole. The same mechanism also allows people to observe solar eclipses, since you can't look directly at those. During the solar eclipse, the little spaces between tree leaves will act like little mini camera obscuras and project the crescent shapes onto the ground. Those crescents are all little tiny images of the sun. If you had good enough eyes and you got close enough and it was projected on something white, you would be able to see the sunspots on those little crescent images. So cool. And that's it. Thank you for watching this video. I feel like I should recommend the video. Well, obviously, you should check out.
All right. So again, I wanted to show you that because that is a real image that is being projected on the inside of that U-Haul, just like the real image I just showed you guys walking around. And that's the same thing that happens inside your eye, is the actual convergence of light rays on your retina. So Again, different than a virtual image. You do need to know the difference between the two. Okay, so how do you know if you have a real or a virtual image? Well, with the lens, you can draw a ray diagram. With a plane mirror, it's always virtual, by the way. With a concave mirror like the one I just showed you, you can actually get a real image, but not with the ones we're going to be talking about, because we just talked about plane mirrors. But with the lens, you can absolutely get a real image. You can also get a virtual one. Okay, it said in the notes earlier that if the object is closer than the focal length, which it was a second ago, that you got a virtual image, and now that it's farther away, you're getting a real image. There's an actual convergence of light rays on the other side of this lens because of the way that it bends those rays. Okay, and so you can see this one's just an animation. But we're going to talk about the different rules for ray diagrams. So you might want to draw some of these on your paper. There are 5 of them. Okay, 5 diagrams that you need to know. You either need to remember the rules or you need to memorize these 5 diagrams. One way or the other, you're going to want to write something down here. Okay, so here is an example of, or these are the rules for a convex lens ray diagram. So first things first, you have some kind of object. Mine's an arrow. Okay, but whatever object you're looking at. Okay, and this arrow, I'm going to draw 3 different rays from this arrow to my lens. So to the center of my lens, this is that optical axis. And so one of them is going to be drawn through the vertex. That's this red one right here. One of them is going to be drawn from, I'm just going to do them all from the top point of the image because that will show me where the top point of the image forms. So one of them is going to be parallel to my principal axis, and then one of them is going to go through the focal point on the near side. Okay, when you draw them, this red one, you're going to draw continuing in the same direction. So you're going to the vertex and then continue a straight line. The one that you drew parallel needs to bend when it goes through the lens and go through the focal point on the other side. And then the one that we drew through this focal point needs to bend and turn and go parallel. Okay, and so you can see that all 3 of these converge in the same location over here, and this is where that image point is formed. Just like in that video, it's going to be upside down because the top was here above the axis and now it's below the axis. Right there, that would be where the top of my arrowhead would form. Okay, now technically you only really need to be able to draw 2 of these rays because they all 3 intersect at the same spot. So if you just want to draw the one that goes through the vertex and the parallel one and see where those intersect, that's fine. But you can draw all 3 of them just to make sure you're in the right point. So again, here's an example of a real image through a converging lens where the point actually does intersect, which we just saw in the last one. You'll notice the real image will be upside down. A virtual image, on the other hand, like the light rays drawn from this one, if I draw them according to the rules, they don't converge over here. However, you would interpret them to do so, your eye would interpret them to do so by tracing back this line of sight, and they do intersect back here. Again, they don't actually, but your brain perceives them to intersect back here. And so you would get this virtual image because the light rays aren't actually converging here, but your brain interprets them as converging here, and then you'd have the image right side up and larger and on the same side of the lens as the object. This is how a magnifying glass works, okay, is with a virtual image on the same side of the glass. Okay, so again, I told you there are 5 different ray diagrams. This is going to show you, in case you weren't sure what a real versus virtual image looks like, this is going to show you real images because obviously we saw it with a mirror a second ago, but you can get real images with the lens as well. I'm not going to watch this whole video. I'm just going to show you a little bit of it so you can see that a lens can produce a real image as well. Okay, so they have a candle and a white piece of paper and a lens. And so they're going to turn off the lights, and they've marked the different points. There's their focal point. There's their optical axis. There's their focal point on the other side. So anyway, they're marking all the points. So you can see here, this is the projection of the actual flame from the candle when they have the candle at f2. Okay, so it's projected on this white screen. Here, you can see it right here. Okay, so I'm gonna pause it for a second. So here's the candle, pretty far away from the lens, and they have the lenses converging those light rays, and here's the actual image, the real image that is formed. It actually does project. Those light rays do converge at this point, and if you put a piece of paper there, you can see it. You can watch it move. You see it in real time, and again, this is how it works in your eye as well. Those images are actually projected upside down on your retina. Okay, and then you can see it change as they move it closer or farther away. Y'all can watch this video in its entirety if you want. This is slide 76, but I'm going to go ahead and move on from here and let you guys go back to it if you want to look at it some more. So I told you there are 5 different cases, basically, for your lenses. So the first case is if you have the object really far away. So if the object is beyond 2f. Okay, and again, you can draw the ray diagram. You'll notice that's what they did here. It's past 2f. They drew one of them parallel, and then it bent through the focal point. They drew the other one through the vertex and continuing straight, and they intersect right here. And so this is where the image formation occurs. Every time that your object is beyond 2f, your image will be in between f and 2f on the other side. It will be upside down, and it will be smaller in size every time. Okay, so again, if you can write down those rules, you can memorize them, or you can just draw the ray diagram and see what happens. Either way will work. But this is the first case. Okay, it will be a real, inverted, and smaller image. Oops, okay, I didn't mean to change that so fast. So again, if the object is placed beyond 2f, you will get a real, inverted, and smaller image that will be between f and 2f. Okay, now that's the first one. The second case is what if you put the object at 2f? So what if the object is at that point 2f? Okay, well then the object that gets formed, again, if you draw the ray diagram, here's my parallel ray. It bends through the focal point. Here is my ray through the vertex. It continues straight. Here's where they intersect. You'll notice that the object is exactly the same size, and it's at the same distance from the lens, but it's just upside down. So if you place the object at 2f, you will get a real image, because the light rays actually converge, that is inverted, it's upside down, and it's the same size as the starting one. Okay, so that's the second case, okay, at 2f. I'm just going to keep moving it closer. What if you put it between 2f and f? Okay, so what if it's between those 2 points? Okay, well, if you place it in between your focal point and your center of curvature, which is what this is, again, you can draw your ray diagram, and you get this giant arrow out here upside down. And so again, you would have a real image that is still upside down, but is larger than the actual object. Okay, so this is how you would perceive it if you were viewing the object in between the focal point and the center of curvature. Okay, in between f and 2f. This is what you're going to get every time. Okay, and it will be beyond 2f. It'll be farther away. And again, you can draw the diagram and see that. The fourth possibility is what if you put the object at the focal point? And this one's kind of weird, because if you draw the ray diagram for this, those lines will never intersect. They are parallel. Okay, and so this forms no image at all. If the object is at the focal point and you are trying to view it through a lens, you will get no image formation. You will not see anything. Okay, it's like a blind spot. Okay, so you're not going to see the object at all at this particular point. I would definitely write that one down. Okay, again, if you draw the ray diagram, parallel and then bend through the focal point, through the vertex, these are parallel. They do not cross. There is no convergence, and I can't trace it backwards either. There's no perceived convergence. There's no image at all. The last case is if you move it closer to the lens than the focal point. And when you do that and you draw the ray diagram, these rays move apart from each other. But your eye would perceive them to be converging back here. Again, the light rays don't actually converge back here. That's what makes this one a virtual image. It also makes it upright and larger. And again, this is what a magnifying glass does. Whenever you're using it to try to view something in a larger size, you're going to see it on the same side of the lens as the actual text or whatever it is you're looking at. It's just going to appear bigger. And it's not upside down. Okay, so virtual, upright, and larger. All right, so those are the 5 rules. If you can draw the diagram, you don't have to memorize the rules. Okay, just remember how to draw the diagrams. Okay, or memorize the rules. There are 5. Either way, you're going to see the questions about them. Okay, so again, those were the rules. If you want to go that route, you can memorize those and always draw it for any case no matter what. But again, if you're prefer to just memorize the cases, you can memorize all 5. All right, guys, you do have an assignment in My Open Math that's due by 11:59 p.m. tonight. It is 1401.2 lens and mirror problem set. You can work on that for the remainder of the class period. You don't have a ton of time, but you can use what time you do have. As a reminder, you do have a quiz on Friday, so your unit summary will be due Friday if you're turning it in. There is a review for that quiz. There's a booklet in addition to the unit summary. And then after you take the quiz, you can work on your video RA project or outline. The outline is due Friday as well. Tomorrow we'll be doing a TEKS review because you have a TEKS test before the quiz. Your TEKS test will be on Thursday. If you guys have any questions as you're working through these problems, please let me know.